All right, it looks like we're recording, so I think we're ready to go. Welcome to day 21 of C and Software Tools class. Today, we're getting close, dangerously close, to a lecture behind in the material. That's okay, we've got some material at the end where we'll cover as much of it as we can, but we'll be okay if we don't get it all done. And we've got one day fewer this semester than we would normally have anyway. So I'll try to keep us as caught up as I can, or catch up as much as I can, but we'll be okay even if I don't keep us on schedule. At the end of class last time, I was trying to convince you, we had just started the day 20 lecture material, and I was trying to convince you that for linked data structures, keeping pointers to the links can be a handy way of working with that data structure. And even though the syntax is a little bit more complicated, it can still let you do everything you could if you were just keeping pointers to nodes. And just to quickly replay some of what I tried to say, if you had a pointer to a node like I'm trying to show in this picture, if you're pointing at that node with a 9 in it, you can use the arrow operator to get to either field of that node. But if you back up and make that a pointer to the next pointer that goes to that node, or if it was the first node, the head pointer inside the list itself, those both have the same type. They're both pointer to node. And if you kept a pointer to that pointer, and that's what I'm using this link variable to stand for, then it would be just as good as a pointer to the node, or at least you could, with a little extra syntax, you could do everything with this link pointer that you could with a pointer that was pointing directly to the node. The reason I say that is if you just stick a star in front of it, it dereferences the pointer, it dereferences the link pointer, and then you get a copy of the pointer to the node. So if you take this star link and you want to look up, you can think of that as, if link is a pointer to the pointer to that node, then star link is a pointer to the node. So you can use that to get any of the fields in the node, again, with just a little bit of extra syntax. If you dereference link and then use arrow to get value, you get its value field. Same kind of thing for the next field. I mentioned already here, we do need the parentheses around that. Otherwise, we don't get the precedence we want in this case. And then I started showing this slide to say, with a pointer to that pointer, there are really two things that you can do to change the pointer structure. If you assign directly to link, then you're deciding what pointer it points to. And that's what this weird picture is trying to show. You can make link point to any pointer you want, or at least any pointer to a node. If you dereference it, then you can use it to change the value of the pointer it points to. And that's what that goofy squid looking thing at the bottom is supposed to show. By dereferencing link and assigning to it, you can change the linking structure of this list. You can make that next pointer it points to point somewhere else. And this would be a handy way of removing that node with a 9 in it, or adding another node in front of it if you wanted. Or you could even add another node after it, although that wouldn't have been hard to do with what we started with the pointer straight to that node. That last part wouldn't have been. To do this, to use a pointer to the pointers in a list, to be able to look at all the nodes and to be able to change the linking structure, we need an easy mechanism for traversing the list. Then we could think of using a pointer like this to go find the node we want. And then, like I said, either remove it or add nodes in front of it or whatever we need to do. So what does it take to traverse a list given a pointer to one of the pointers inside the list? Well, basically, if you look at my figure up at the top, I need to be able to take this pointer to the next pointer that points to the 9 node, or maybe easier to say, I need to be able to take this pointer that's pointing inside the node with the 103 in it, and I need to move it ahead. I need to make it point to the pointer inside the node that has the 9 in it. And this effectively moves this pointer one node ahead in the list. And then I could use this as part of a for loop to traverse the list. So what does it take to do this? That's what I'm trying to show with the syntax down here. I want to take this link pointer and I want to, like the bottom picture shows, I want to make it point to this next pointer inside the next node. Well, if I take link and I dereference it, now I've got this next pointer, or at least I've got the value of the next pointer inside this node. If I use arrow to get, if I use arrow next, then I'm getting the next pointer inside this node with the 9 on it. Same thing we had on the previous slide. If I just put an ampersand in front of that, then I'm asking about the address of the next pointer inside this next node, inside this node with the 9 in it. And if I take that address and assign it to link, well, now I'm saying I want link to point to that address, or at least to point to that pointer. And like my figure at the bottom shows, this operation will move link ahead so that now it's pointing to the next pointer inside the next node. And like I said, if I put this inside a for loop, I could use it to march down that list one node at a time, looking at the next pointers inside the nodes rather than looking directly at the nodes, or said better, looking at the pointers to the nodes rather than looking at the nodes themselves. Why is this possibly a good idea? You can use this to change the linking structure in the list. Like I said, if you take link and dereference it, then assign something to that, you're changing the contents of the pointer it points to. So if you wanted to remove, for example, if you wanted to remove this node with a 9 in it, you could just get a copy of the next pointer inside that node. And here's the syntax for doing that. Take link, dereference it, use arrow to get the next field inside the node it points to. And then if you take that node or that pointer and copy it into the pointer that link points to, then you've just made this pointer, like my little red arrow shows here, you've made it skip over this node. You've effectively removed this node from the list. If the space for all these nodes was dynamically allocated, you'd also have to worry about, well, if you were trying to delete that node, you'd have to worry about freeing that memory. But this gives you a handy way of manipulating a list without having to handle things in special cases. That's maybe not a big deal for a list because you've really only got one special case, and that is, am I removing the first node on the list, in which case I have to change the head pointer to remove it. Whereas if I'm removing any other node on the list, I have to change the next pointer out of its predecessor. But if you use code like this, you don't have to treat the first node as a special case. Whatever node you have to remove, you just have to change the node pointer that points to it. I started to say this is a small gain for a linked list. This can save us a lot of code if we're implementing something like a binary tree, where every node has 2 pointers, a left and a right pointer, and being able to treat both of those, not necessarily exactly the same, but being able to manipulate them both using some of the same code can really shorten our implementation of a binary tree. So we're going to build a binary tree using some of these same tricks. We were just warming up with the list example. But for a binary tree, if I wanted to build that, I could still think of it as being made of nodes. And that's what this top struct, you can think of it showing. I'm going to have a struct, every node representing a node. Every node has a value, an integer value in this example, but it also has a left and a right pointer pointing to its 2 children. And I'm taking for granted that you already know about binary trees. We're going to keep them sorted left to right based on value. So larger values will be in the right subtree, smaller values will be in the left subtree. We're not building, I know many of you are in the data structures class where you've probably seen maybe several mechanisms or several ways of building a balanced binary tree. We're not going to try that today, but we'll just build a binary tree and we'll get whatever balancing we happen to get. So I've got a struct for representing a node. I made a short name for it using typedef, so I don't have to say the word struct over and over every time I want to talk about a node. And then I've got a small struct representing the whole tree. And it really just contains a field for the root pointer, but we've got room for other stuff in this tree struct if we needed other values or other parts of a data structure to keep up with that. Questions before we talk about what we're going to do? All right, so building a tree out of this structure would look something like this. We'd have an instance of the tree struct. It has a root pointer that points to a node. Any node could have a left and a right pointer. And like I said, for the rules of a typical binary tree, the left pointer points to a subtree with keys that are all less than the key at that node. And the right pointer points to a subtree with keys that are all greater than or equal. I guess it would depend on what you wanted out of your tree. If you wanted to have duplicate keys, then you'd have to let them fall on either the left or the right. If you didn't want to have duplicate keys, you could just say everything to the left is less and everything to the right is greater. It's a small detail, but it's probably worth thinking about. All right, let's say we're going to write some code for inserting a value to this tree. And we're going to use the trick we just talked about with manipulating a linked list by keeping up with the address of the pointers inside that list. We're going to pretend we have a link variable just like we had, and we're going to think of that link as pointing to or keeping up with a particular node. So I'm going to start by looking at this node at the top, the root node with the 21 in it, but instead of and in C, I certainly could have had a pointer directly to this node, but I'm going to try to shorten my implementation by keeping a pointer to the pointer to that node. And I claim this is going to make it a little easier to manipulate the tree. And in this case, we're just trying to add a node to the tree. So I've got a pointer to the root pointer. Let's pretend I want to insert the value 30 in this tree. Well, I look at 30 and I compare it to the value at the root node, or I guess more generally, the value at the node that link is keeping up with. I said keeping up with because the right way to say that is the value at the node that's pointed to by the pointer that link is pointing to. And even though that's technically correct, that's a lot harder to say and follow. So I'll just use the term link is keeping up with a node. Right now it's keeping up with the root node, the node with 21 in it. But since 30 goes to the right of 21, when I find a place for that 30 to go, I'm going to descend this tree. And since 30 is bigger than the 21, I want to descend it into its right subtree. So when I notice that 30 is bigger than 21, I want to move link ahead and now have it point to the right pointer inside that root node. And then I think of it as keeping up with it now, this node with the 50 in it. 30 is less than 50. So descending the tree, I want to move that link pointer so it now points to the left pointer inside that node with the 50 on it. And I think of that as, well, now link is looking at. I should use this word looking at instead. Now link is keeping up with this 42 node. 30 is less than 42. So I'm going to move down, and now link is pointing at the left pointer inside that node with the 42 in it. And now I'm done, or at least I'm done finding where to put this node. Because once I find a pointer that's null, I've kind of found a subtree that doesn't have anything in it. And that's where this new node goes. I can allocate space for a new node. This doesn't fit on my figure, but my next slide shows code for this. I can allocate space for a node, put a 30 in it, and then change the pointer that link points to. This one I've boxed in red here. I can change that to point to the new node. And the nice thing about this is whether I had a left pointer out of this node or a right pointer out of this node, as long as I knew its address, I could make that pointer point somewhere else, grafting on this new node without having to have if statements that say, well, should you modify the left pointer or the right pointer here? What's it take to do this? Well, this is the code that we were just talking about. This is all it takes to insert into a binary search tree, as long as you're not worried about balance. So this could give us an unbalanced tree depending upon the insertion order. But I think it's a lot simpler than what we, or at least a lot shorter than what we would get if we had to write different code for looking at left pointers and right pointers. Certainly we could do it that way, but this simplifies some things. So for insert, I'll talk you through this code real fast. You give me a pointer to a tree and you tell me the value I want to insert. And then everything from here down to the end of this while loop is looking for where I'm going to put that node. I start out just like in our pictures. I start out with link pointing to the root pointer. And we said once you find a null pointer, that's where you're going to put the node. So as long as link doesn't point to a null pointer, well, I can take link dereference that. So that'll give me the value of the pointer it's looking at. And as long as that evaluates to true, it's non-null. So I keep descending the tree. I compare the value I'm looking at, sorry, the value I want to insert with the value of the node I'm looking at. And if they match, here I've got it returning false. The way I wrote this code is we're not going to permit duplicate values in the tree. So if you try to insert a value that's already there, it tells you false. We could have written this differently. That's just what this example does. Otherwise, I look at it and see, well, the value I'm trying to insert, does that go to the left or the right? And then here's kind of where we save a little bit of code. If it goes to the left, then link gets the address of the left pointer out of the node I was looking at. Otherwise, it gets the address of the right pointer out of that node. And that's kind of, if you let me back up a slide or two, that's kind of what I kept saying as we looked at the code, or as we talked about the code it would take to descend the nodes of this tree, parent to child. And then once I've done this while loop, I'm just about done. I found a place where I'm going to put the node, so I malloc some space for a new node. I fill in its value field, and I fill in its left and right pointers to make them null. It's a leaf node, so it's not going to have any children yet. The space for this node is malloced, so it's uninitialized. So if I don't set the left and right pointers to null, it they might have a non-null value, and it might look like this node had children when it shouldn't. So I could, here I just set them to null. I could have done some other things, like I could have used calloc instead of malloc, but that would have been a little more expensive. And then at the end, I'm almost done. I just need to link it into the tree. Link is a pointer to the pointer out of the leaf of the tree. Let me try to say that better. Link is a pointer to the pointer I need to change. So if I dereference link and then assign that to n, now that pointer out of one of the leaf nodes of the tree, now it points to this node. My picture makes this easier to talk about. I dereference link and then I assign that to n. So that changes this red pointer here, the left, well, in this example, in this picture, the left pointer out of this node with 42 on it to point to that new node I made. And that's our last example of how you can use pointer-to-pointer tricks to simplify some code for linked data structures on one of your exercises. I think it's exercise 20 that will be due this weekend. You get to practice that a little bit yourself. And hopefully this little bit of time we spent reminding you of that, hopefully that'll pay off when you get to work on that exercise. Any questions before we move on? All right. While we're talking about data structures, I wanted to revisit a topic that we touched on briefly, and that is how we can build things that kind of behave like object-oriented code, but building them in a language that doesn't really include language support for object orientation. I was a developer in the days before C++, and a lot of code was being written in C in those days, but people are already trying to use object-oriented techniques. They had advantages. You could do this in a language like C, it's just you had to do a lot of the work yourself. Newer languages like Java and C++, and a lot of languages that also include object-oriented features, they make it a lot easier for the programmer because the language has built-in features for that. We're going to figure out how to do some of that ourselves. And some of the point is, well, in varying degree, C programs really do this kind of thing. If you look at the code for parts of an operating system, often those are written in C or with large chunks of C code. And inside an operating system, you need mechanisms for abstraction, the kind of thing that objects provide, at least abstract objects provide in an object-oriented language. So what we're seeing here will be kind of a selection of common tricks for writing code in C. And we'll also be understanding how this really works in an object-oriented language. The tricks that we're going to talk about here are what languages like C++ and Java do underneath. When you call a function that can be overridden, we're going to figure out how we could do that in C. And secretly, Java uses very similar tricks when you're implementing a class and then making a subclass and overriding methods in that subclass. I've got a single motivating example that tries to show all of this off. And I think of it as being kind of like a spreadsheet we're going to build. The spreadsheet is going to be an array, or at least it's going to be implemented with help from an array. But the place where the object orientation is going to come in is what we put in the cells. I'm going to build a little pretend inheritance hierarchy for the cells. And that's what I'm trying to illustrate here. You could have a cell that's essentially empty, in which case it really just needs to keep up with how big it is, how wide it gets shown in the spreadsheet. You could have a cell that has a floating point number in it, that has a double value. We'll pretend that's for representing money, for representing monetary values. And later we'll have a cell type that can have an arbitrary string in it. So we will need, again, a little inheritance hierarchy. At least we'll need to figure out how to build one ourselves so that we can fill a spreadsheet with any type of cell. So how do we build an object in a language like C, or something that can do all the normal stuff an object could do? Well, no surprise. Every object is going to be a struct. We're going to start with just the first two. We're going to have a generic cell, and that's going to be kind of like our superclass for all the different types of cells we might want to make. So it's kind of a generic version of a cell. I'm going to build a cell so that it just has a width field. Different cells can need different amounts of horizontal space. We'll measure that in characters. So when I print what's in the cell, how many characters do I need? But we're also going to have money as a type of cell that not only keeps up with a width, but also has a numeric, a floating point. I think it's going to be floating point, numeric value for a particular amount of money. We'll say in dollars. How are we going to build this? Well, we're going to build, like I said a moment ago, we're going to build two structs, one for the superclass cell and one for the subclass money. And we're going to organize them so their memory is laid out like this picture shows. Cell will just have a width field, and that'll be its first field. Money will have a width field, and it'll also be its first field, but it'll have some extra stuff, or if it needs additional fields, like its value field, we'll just lay out the struct so that comes after the width field. Why is this a good idea? Well, if you were looking at either of these structs and you had a pointer to it, if you dereference that pointer, at least with the superclass cell, you would expect to see an integer width field right at the start of the memory where that struct is stored. If you had a pointer to a money object and you dereference that pointer and looked at the first integer right where the pointer points, you'd see the same thing. You'd see an integer width value. So if you were looking at either the superclass or the subclass, you could treat them both as an instance to the superclass because in memory, they both look like a cell. They both have a width field right there at the start of the struct in memory. Now, sure, the subclass might also have some stuff coming after that, but if you were looking at them both as if they were the superclass, as if they were a cell, you wouldn't even be looking at that stuff. You would expect to see a width field right at the start of the memory, right at the start of the memory for that struct, right at the memory you get when you dereference this pointer. So they both look like an instance of the superclass. If we had to build structs that behave like this, here's what our implementation could look like. We'd just make a struct for the superclass for cell, and then we would make a struct for the subclass. And we would be careful to make sure it started out looking just like a copy of the superclass. So like, and I'll say this quickly because it's probably obvious, superclass cell has a width field right there at the start. My subclass has a width field right at the start, but it has some other stuff that I'm going to add, but I'll add it afterward. Languages like Java use this same trick. When they're storing an object, they organize the memory for that object so that all the stuff in the superclass is at the start of the memory for that object, and anything that's added by a subclass is put after it in memory. So if you're looking at an object and you're trying to treat it as an instance of its superclass, all the stuff you expect to see will be right where you expect to see it in memory. The thing we don't get that object-oriented languages give you is we had to do this ourselves. I said, when we're making this thing that we expect to work like a subclass, we had to be careful and make it start out with a copy of exactly what the superclass has. A real object-oriented language would do that for you. You would be able to say, I want to make a money struct, and I want it to inherit from this other struct. And the compiler would make sure that it gets copies of everything that its superclass is supposed to have. Another disadvantage that you'll see on the next slide is you and I know that money is supposed to work like a subclass of cell, but the compiler doesn't know that. It doesn't try to notice, oh, these two structs start out the same way. It means that as far as the compiler is concerned, these are two completely different types. In an object-oriented language, if you started with a pointer to money, or in Java, a reference to money, the language would automatically let you treat it as a reference to a cell, as a reference to its superclass. But like I said, we're doing this trick in C, but the compiler doesn't know what we're trying to do. So whenever we convert an object of a subclass to its superclass, we're going to have to use a typecast. And when I say object, I mean a pointer to one of these things. For this to work, we're going to need to work with these objects via pointers to them rather than having, rather than directly using values of these object types. That's kind of why in Java, whenever you work with an object, you're using references to that object. Because in Java, we don't have things that are called pointers. We have references, but as you can probably see, they are secretly very similar to the idea of a pointer. All right, so we're going to build a couple, just to get started, we're going to build a couple of objects, or a couple of types. We're going to treat them as a superclass and a subclass. They're each going to need a constructor. To make an instance of this object, what would it take to simulate a constructor? Well, we don't have a new operator in C, but we can make our own function for building either a cell or its subclass money. And if you wanted to work like a constructor, you could pass in parameters that are used to initialize the new object. If you wanted to work like a constructor, you could have this function return a pointer to that object. And Java, that would be like returning a reference to it. And while we're inside this function, we need to allocate space for that object. So for cell, its constructor, sorry, that was an accident, its constructor might look like this. We'll malloc space for a cell, we'll fill in its value field, and then we'll return a pointer to that object. And over on the right, you can think of that as building a little object with just a cell field in it, initialized to whatever you pass in. For the subclass, for money, well, we're still going to initialize the width field, so you'll pass in width, but we'll also have a value field for dollar amount. I guessed a moment ago when I was looking at this that dollars was going to be a double, but looking at this code, it looks like it's an integer. Probably I could have noticed that on the previous slide. Yeah, the value in a money slot is integer. So I guess that's, we'll see in a moment Sorry, I wrote this code, but it's been a little while since I wrote it. Well, I'm guessing that's money expressed in cents rather than in dollars. So we'll fill in the width field and the value field and return a pointer to that. Notice when I'm allocating space for money, I'm asking for enough memory for an instance of the money class or struct. And so I'm going to get a little more memory than I would have if I just asked for an instance of the superclass cell. Questions before we move on? All right, how would we use this? So my next example builds a spreadsheet, a two-dimensional array containing cells. But for this to work, I need to keep up with those cells via a pointer to them. So if I wanted to make a spreadsheet with 2 rows and 3 columns, I could make a array like I've got at the top. You can read that array's type as sheet is a 2x3 array of pointers to cells. And then I fill in each of its elements with a new cell. For the ones in the left column and the right column, I just make those instances of the superclass. I'm calling the constructor we had in the previous example. For the middle column, I make instances of this money class. So for the top, I want a width of 12 and a value of $3.75. For the bottom one, it's a little more expensive. Notice money returns a pointer to the money class. But like I said, C doesn't know that we're trying to use that as a subclass of cell. So to turn that into a pointer to its superclass, I have to do a typecast. As long as I'm just using it as a pointer to cell, it should work fine, because like my picture shows, whether you've got a pointer to a superclass cell or a pointer to the subclass money, if you dereference that pointer and look at memory, you're going to see a width field in either case. So here's how we make a spreadsheet that uses this inheritance hierarchy we're pretending to make. How do I use it? Well, we'll start out simple. Let's say I just want to print a spreadsheet with dividers around it, kind of like my picture shows. Well, I've gotten a nested for loop to iterate over all the cells. To make the syntax a little easier to look at, I go get a pointer to the element at row I in column J, and I copy that to a local variable. And then if I want to print out enough spaces to leave room for that cell, this is a syntax I don't think we've seen yet, but %s would print any string. %s lets you specify the minimum field width with a parameter. So for printing the cells wide enough to take all the space they need, I just use the width field of that cell. And whenever I get a pointer to a cell, whether it's the superclass or the base class, if I go look at the width field, or I look at the first integer right after where that pointer points, that should be the width for that cell. So this is kind of like looking up a field in an object. Using inheritance, whether it's the superclass or the subclass, they all should have a width field that's in the same relative place in memory. Now, to fit this on the slide, I had to simplify some of this code. So I took out the code for printing the vertical bars and the rows of dashes. I've posted this example code, so if you want to look at it, it takes a little bit more space, but the real code in the examples includes the printouts for that. I prepared before class to run these examples. And this first example is spreadsheet1.c. I think it's already compiled, so let's give it a try. Yes, so just like my picture shows, inside, I'll show you the code real fast, but we definitely won't read through all of it. This is just a nothing up my sleeve kind of demonstration. So you can see here we're defining the superclass struct, and here's its constructor. Here we're defining the subclass we just talked about. And you can see I've got a lot more comments in the example, in the actual code. I usually take those out to put them on a slide just so stuff fits. Constructor for the subclass. This is just some helper functions to help print out the spreadsheet. Here's the same code we just looked at for making the spreadsheet and filling in its cells to point to stuff. And here's the code we just looked at for printing out cells of the right width. And then the next little piece is some code we still have to look at. And that is before we exit. Once we're done printing the spreadsheet, or I guess in general, once we're done with whatever we want to do with that spreadsheet, we need to clean up after it. All those objects were mallocked. So unless we want to look like we have a memory leak, we need to free space for those. Fortunately, whether it's an instance of the superclass or an instance of the subclass, all of its memory is one big block. So it only takes one call to free each of those. So freeing memory for these cells just takes a nested loop. I can look at the pointer inside each element of my spreadsheet and call free on that. And that'll free up, again, either an instance of the superclass or an instance of the subclass, because all free needs is a pointer to the start of a block of memory. All right, so I want to dress this up with some additional features. So far, all we've done is we created something that kind of works like a superclass and a subclass, but to use it, you have to directly access its fields. We saw on this previous slide, we saw, well, you're going and looking at the width field directly. And sure, that works with either the superclass or the subclass. But typically, in an object-oriented language, you would want a mechanism for encapsulation. You wouldn't ask for or you wouldn't access the field directly. You would probably want a method that lets you access that. So what does it take to implement a method or something that works like a method and one that can be inherited? Well, this part is extremely easy because we kind of already planned for this. If we want to make a method, kind of like we talked about a few weeks ago, it's going to have to be a plain old function. Later in C++, when we talk about that, we'll call this a free function. It's just a function that's not inside anything. So we'll make a function. We can make a function called getWidth. Normally, an instance method works on a particular instance of an object. Well, that happens automatically in languages like Java. But here, if we want it to work on a particular instance of a cell, we're going to have to pass that in as a parameter. And if that method needs a return value, that can just be a return value for this function. So what I built here is kind of like an instance method on cell on the superclass, but it also will work like it's inherited by any of the subclasses, because like I said, we already planned for this. Whether you've got an instance to the superclass or its subclass, they both have a width field that shows up in the same place inside that struct. So if you call this getWidth function and you give it a pointer to either of these, when it goes and looks for the width field, it will find it in the same relative spot in memory. So it'll be able to return its value. So this will work like an instance method. And as long as you built your subclasses the right way, it'll automatically work on any of those subclasses. So it's kind of like you inherit this method for all the subclasses. If we wanted to use this, what would it take? Well, the only change here is, here's where we're printing out the contents of the spreadsheet. Previously, we were just going and getting the width field ourselves. Here now we're calling that method for the width field. The rest of this code is the same, and this will work just fine, whether you're giving it a pointer to the superclass cell or one of its subclasses. We can't force encapsulation. In Java and in other object-oriented languages, we typically have attributes like public and private and protected that the compiler tries to respect to prevent us from being able to access stuff we shouldn't. In C, we're not going to get stuff like that. If you have a pointer to some piece of memory, there's really nothing to keep a piece of code from looking around inside that memory. Even if they didn't have the definition of the struct you're using, they can still see the contents of that memory. And I guess if you had an attacker that was trying to figure out what's in your object, you're not really going to be able to keep them from looking at what's in your object, unless you were willing to do some kind of encryption of what's in memory. Here we've got regular methods, ones that you can't override. What if you wanted to be able to build a method that you could override? So the idea is, and that's kind of the missing thing from our spreadsheet so far. All we're doing is printing out cells, but they don't have anything printed out inside them. If you let me back up a slide, this line right here, I didn't say it, but when we print out what's in a cell, this empty string here just gets printed as an empty string, but padded up to whatever width it's supposed to be. So we're not really printing out what's inside the cell. For this money cell, we should be able to print out the value of the monetary value of that amount of money. For later, we'll make a cell that can hold an arbitrary string, and it needs to be able to print out whatever that string is. So since different cells need to be able to print themselves differently, we need to be able to make a function, a method that every cell has, but when we call it, I want different behavior from different types of cells. And again, this is an overridable function. It's a function that we can have a version of that for the superclass, but then as we make subclasses, they can each have their own version of that function. How are we going to do this? Well, here I'm going to show you a way of doing it that is a little more expensive than how this is really done in an object-oriented language, but it shows the same main ideas, and the tricks to make it less expensive are really just a better, a small change from what you're going to see today. So since different types of cells need to be able to print themselves differently, they need to each have a print function, but when you call that print function on the superclass or the subclass, you need to get a different implementation of that function. The way we're going to do this is every cell can carry around a pointer to its print function. Every cell, whether it's the superclass or the money subclass, has a pointer to a print function. That pointer points to, well, for cells, for the superclass, maybe we'll just have them print out a bunch of spaces. Maybe the superclass, well, I mean, it doesn't store any values, so it'll just print itself out as a blank cell. For money, it needs to print out a monetary amount, so it'll have a print function or it'll have a pointer to a function that prints out a dollar amount of money. In C++, or in Java, we say we're overriding a function when we fill in different versions of that function for subclasses. In C++, they call this a virtual function. And we might get to see that when we talk about C++ briefly at the end. In Java, whenever you make a class, by default, its functions are overridable. In C++, it's the other way around. If you want a function and you want to be able to override it, you have to mark it as a virtual function. And this kind of reflects C and C++'s orientation. You'll see in a moment, it takes a little bit more overhead to call a function that you can override. So in C++, if you want to pay that overhead, you kind of have to ask for it. Otherwise, you're going to get a function that's not overridable, but it is computationally a little cheaper to call. So now our cell class has one more thing in it. It has a width field like we've already talked about, and every cell has a pointer to its print function. Subclasses of cell need to make sure they follow the layout of their superclass. So now money as a subclass needs to start with two fields that look exactly like its superclass, and then anything extra they have can come after those fields. And as long as we do that, a subclass of cell, this money class, in memory will look just like its superclass, except with some extra stuff afterward. If we put in a function like this, one that was overridable, one where the object carries around a pointer to its version of that function, well, the superclass would look like this. It's got a width field, but before that, it has a pointer to its print function. And when you call its print function, you have to give it a pointer to the cell itself, to the thing it's supposed to print. We said that the print function in a cell needs to just print out a bunch of blanks. So this is the function I'm going to use for that. This print cell function just prints out a bunch of spaces for however wide that cell needs to be. So it'll look like that cell is empty. When you make the superclass cell, you need to fill in two things. Its width field, which we already had, and now you need to fill in its print function. Every time you make an instance of the superclass, you're going to fill in its print field. That's this function pointer up here, so that it points to the print function for a plain old cell, the function we defined up here. For a subclass of this, well, for defining its struct, it'll start out looking just like its superclass. This extra value field that it needs, we'll put that afterward. It'll have its own print function, but instead of just printing a bunch of spaces, it'll print out a dollar amount. It looks like I don't print a dollar sign in front of it, and that would probably be something good to add to this example, but it just takes whatever's in the value field and prints it out as dollars and cents. And I've just got a format string that does that, prints out, divides it by 100 and mods it by 100 to get dollars and cents, and then prints those out with a dot in between them. Oh, sorry, I lost my train of thought. And now the money constructor has to allocate space for money, fill in the width and value field, just like we were doing before, but it also needs to fill in the print function. But unlike the superclass, instances of money, their print function will point somewhere else. So now if we make this same kind of spreadsheet, I updated the picture here to show what you're going to get in memory. If you build a spreadsheet using this version of the implementation, every cell is going to have a pointer to potentially a different type of object. They all have a print function, and when you call that, well, for the superclass, you're going to get a particular function, the one that prints all the blanks. If you go get the print function for a money cell, you're going to get a pointer to a different function. What does it take to call a function given a pointer to one of these objects? Well, that's this red code here in the middle. Same as before, to make my life easy, or to make the code a little easier to look at, when I'm looking at cell IJ in the spreadsheet, I go get a copy of that pointer and put it in a local variable C. And then to call the print function, well, the print function is, there's a pointer to the print function inside that object. So this first bit, take C, go get its print field. Now you're getting a pointer to a function. If you want to call the function it points to, you put parentheses after that, just like we've always done for pointers to a function. And then that function needs the cell it's supposed to print. If you let me back up a slide, yeah, print money. Now we have a pointer to that for a money cell at least. It expects a parameter that is, tell me the cell I'm supposed to print out. Give me the instance I'm supposed to print. So even though we already used C to get the pointer to its print function, we also have to pass it to that function. So that's why it shows up twice in this call. In a real object-oriented language, it would do this, we wouldn't have to explicitly pass this in. The compiler would add code to do that for us. But here we're having to do all that ourselves. We have one more version of this program to look at. If you want, I think we skipped over a version, but I think spreadsheet 3 does what we just looked at. It makes a spreadsheet with these two different kind of cells, and now the money cells print themselves out in the middle column. Questions before we see our one last thing, I think? To make this more interesting, so I won't say I lied about that, but to motivate this one last thing, we're going to make one new subclass, and it's the one we saw in our first example, a subclass that we'll call it text, and it can hold an arbitrary string that gets printed out inside a cell. Here's how we're going to store it. Well, since it's a subclass of cell, it has to start out looking just like its superclass. So it'll have a print function pointer and a width field. It'll have a pointer to a string of arbitrary length. We could have stored that string right inside the text struct, but then that would have limited how big it could be. Instead, we'll store a pointer to a string elsewhere in memory, and then we can allocate that memory to hold as big of a string as we need. This, implementing the cell won't be too bad, but just looking at this picture, it reveals something new that we're going to need. If you remember, previously, when we were done with a spreadsheet, we just went through all of its cells and called free on all of them. But that won't work for this kind of cell. Imagine you had a pointer to this text object and you just called free on it. Well, that would free all the memory for the text struct, but it would have a point inside. It's got a pointer to some memory holding a particular string, and it wouldn't automatically free that memory. I think what we're seeing here is, in general, freeing space for an object, the right way to do that depends on how the object is stored. If you think back to some of our previous, I guess it'd probably be project 4, once we had allocated, using malloc, we had allocated some kind of data structure, we would often write a function to help free that data structure, because freeing it might require freeing the stuff inside it, and then freeing, for depending upon what it was, maybe freeing the stuff inside those objects. We've kind of got the same thing here. For text, it needs to free the content, the memory for the string, and then free the memory for the text object itself. So this is kind of like what we saw with the print function. The right way to free space for an object depends on the object. So when it's time to free an object, we need something that behaves kind of like the print function, kind of like what C++ would call a virtual function. We need a way of freeing something that we can override so that subclasses can free their memory the right way for that subclass. This is nothing new, although it gives us a new term. We're really seeing that we need a virtual destructor. We need a way of freeing memory for an object, but the right way to do that depends on the type of that object. So we'll handle this by adding a new overridable function. Instead of just having a print and a width, now every cell is going to have a destroy function, but we want it to be one that we can override. So it'll be a pointer to a function that frees the memory the right way for whatever that type of cell is. For the base class cell, it can just free object for the struct itself. Same thing for the money object. But for text, it's going to have to free, its destroy function is going to be a pointer to a function that frees the memory for the string and then frees the memory for the struct itself. If you look at the example, it shows all of this code. It's kind of getting to the point that I can't fit it all on a slide anymore, but I'm trying to show you the important parts here. So now for the superclass cell, it's going to carry around pointers to 2 functions. Here's what you do when you want to print me. Here's what you do when you want to free the memory for me. In its constructor, it's going to fill in that destroy. I picked the name destroy for this function to free the memory for a thing. It's going to fill that in with a pointer to this function up here that just frees the memory for that cell struct. Money's going to be the same way. Its destroy function is going to be simple, but this new object that we talked about, text, it can do something fancier with its destroy function. Text, well, now the superclass has 3 things, so it's going to start out with 2 function pointers and a width field, and then it's going to add a char pointer to hold a pointer to whatever string you want. When you print what's in a text field, it'll just print whatever's in its string field, padded to whatever the width of that field is supposed to be. When you free the memory for a text, and this is kind of what we've been talking about, it'll free the memory for the string that's pointed to by the string pointer, and then for the struct itself. So it'll, in my picture, it'll free this, and then it'll free the whole struct. In the constructor for text, when you make a new text object, you'll, just like money, you'll tell it the width, you'll tell it the string that it needs to print. It'll fill in its 2 function pointers. Here's how to print text. Here's how to destroy a text object. That's the code we just looked at on the previous slide. It will make a copy of whatever string you give it. So when you call make text, you give it a string. and then it copies that into malloc space to hold a copy of that string. Now, we can make a spreadsheet that includes 3 types of cells. The left-hand column is all the superclass. The middle column, I've got an amount of money. The right-hand column, I've got an amount of, or I've got text objects for those. The nice thing is, whenever I print them out, this code didn't have to change at all. All of these objects, no matter what type they were, they have a print pointer, and it's in the same place in memory. So kind of like you expect out of an object-oriented language, I can extend the inheritance hierarchy. I can add new types of objects, and client code doesn't have to change because the thing it was doing to call the print method, to call this print function for each object, that same code still gives it the print function for new types of objects that it didn't even know about when we wrote this code. But the new thing that we have is how to free these objects. Now every object, instead of just calling free on it, every object has its own function to free its memory. So if we want to clean up after all of these objects, we can just go through the whole spreadsheet, get a, well, here to simplify it, I'm getting a copy of the pointer in each cell, and I'm calling its destroy method. And just like we were doing with the print method, I take a pointer to the object, I get a pointer to its destroy function, so that's what this part is doing. But just like the print function, that destroy function needs a parameter. It needs to know the object it's supposed to destroy. Well, it can't get it from this C over here. I was just using that to get a pointer to that function that I want to call. So I have to also pass that in as a parameter. And that is all I've got to say about object orientation in C. Our plan is our last project for the semester, which will probably be a little bit smaller than previous projects. You'll get to use some tricks like this in that project. Questions before we move on? All right, you may not believe, question, yeah.
So is there ever like a situation where the compiler could like optimize something where like the memory would get restructured in a way that this wouldn't work?
You mean like, will the compiler, I think your question would make sense if the compiler was willing to rearrange fields of a struct. Like if it looked at the struct and said, you know, it'd be much better if you put these fields in this order. And I know we talked about that already when we were talking about padding. And we probably said, yeah, it'd be neat if the compiler did that. But if it did, it would break this. So I'm going to say, even though having to put padding in a struct is unfortunate, having a guarantee that the order that you put the fields is respected by the compiler, it seems like that makes it, that gives us back an advantage for that. I'm going to say, as long as you don't switch compilers, you don't have to worry about the compiler messing with your memory layout in a way that would break this. If you had 2 different compilers and you compiled the superclass on one compiler and then compiled the derived class, the subclass, on a different compiler, it's possible that the fields could, in fact, I would say you don't have any guarantees then. But as long as the compiler respects the order of the fields that you gave and it is expected to, then this should work. Other questions? All right, I was about to say, you may not believe it, but we've caught up a little bit. I've been looking at when the switch occurs between the stuff we should have already covered and the stuff we're supposed to be occurring, and we're a couple of minutes ahead of where we were last time. All right, so here's where we're supposed to be today. We're supposed to be talking about security. And this is going to come in a few different kind of categories or a few different big topics. First, we're going to have kind of a sweeping reminder of mistakes you can make when you're coding in C. And that's kind of the intent there, is we're going to sneak in some term definitions. I'm going to try to make you aware of maybe some potential vulnerabilities that you haven't thought about. And the reason that matters is if you're writing code, you need to be aware of those potential mistakes, some of them common mistakes. So we'll look at some bad code to see what those mistakes could be. And then at the end, we'll look at encryption. That's a little bit of a change of topic, but encryption is one of our most reusable mechanisms for trying to provide security. It doesn't necessarily fix program vulnerabilities, but it is a way to try to keep secure information secret. So we'll spend some time at the end talking about what we can do to use encryption tools in our program. So first we'll visit, I call this the island of bad programs. I'm just picking a silly name for what we're about to do. And that is, you know that as a C programmer, it is easy to have mistakes in your code. It's easy to mess up and have a buffer overflow or access memory that hasn't been initialized yet, or access memory you're not supposed to access. And in a language like Java, the runtime environment is built to try to catch it when you make some mistakes like that. But in C, the philosophy is that it's up to the programmer to think about that. If you are worried about a potential buffer overflow, then you need to fix that. You need to make sure your code can't buffer overflow. And the advantage of this is we can write some much faster code in C because the execution environment isn't automatically checking all this stuff for us. But it means that you have to be thinking of a lot more stuff as the programmer to make sure that you don't have some vulnerabilities in your code. Where do errors come from in programs? Why do these vulnerabilities get left in? Well, there are four big categories of mistakes that get, and kind of reasons for those mistakes, and I've listed these here. Some of them, some vulnerabilities are just because of programming errors. You try to access a pointer that doesn't point to anything. And maybe those are the most common, but they usually, if they're a bug, they might show up and give you a chance to fix it. Often, programs can have errors because we assume the input is always valid. Failing to validate it, failing to think about potentially malicious inputs, can leave vulnerabilities in our code. We might have data that should be secret that we accidentally expose. And often we might end up using APIs, we might end up using features of our language or our execution environment that we don't fully understand. And that might expose things that shouldn't be exposed. And especially that, maybe those last, I'll actually say those last three show up in any implementation language. If you fail to validate user inputs, or if you always assume that they're going to be valid, that can leave vulnerabilities in a Java program probably just as easily or about as easily as a C program. So I wrote a bunch of bad code, and I think it's all posted. It's certainly all here in the slides. Normally, if we were meeting face-to-face, I would invite people to tell me what's wrong with this code. In the interest of time, I'll tell you what this code is supposed to do. And I know that when we're meeting online like this, it's kind of harder to go back and forth about this. So I'll go ahead and just tell you what's wrong with it. So this function, the intent of it is to read a block of data from a file, where a block of data is defined by, let's say it's a kilobyte. It's whatever this constant block size is. So you call this function, you give it a file, it dynamically allocates space for a whole block of data, and it returns a pointer to that block to you. So it mallocs space for the block of data. It checks to make sure that the block of data got allocated, and we'll pretend we have a policy of just returning null if something goes wrong. So if I can't allocate the block, I return null, so it didn't work. I try to read a block of data. This is that fread call that you've already seen. It's for reading however many bytes of data you want from the file into this block. So if I successfully read that much data, I return the block. Otherwise, I return null. What's wrong with this function? Well, there's a path through it that involves a memory leak. And it's right here. If we couldn't get the block of data, or if we couldn't malloc enough space to hold the block of data, we return null. But there, we didn't even allocate the block, so there's no leak. But down here, if we've allocated the block and we can't read as much data as we wanted, we return null without freeing that block. A takeaway from this is, and we kind of talked about this when we were talking about non-local jumps. We need to make sure that if we've allocated resources, every path of execution through a function or through our code worries about freeing those resources. And here there's a path where you return here where we don't free that block of memory and we don't give it to anyone else. We don't return it, so no one's going to be able to free it. So this is definitely going to be a memory leak. Another bad program. So here we're doing something similar. We're going to read some data from a file, but instead of giving the function a file that's already open, we give the function a file name. It counts on opening the file. If we can't open the file, it returns false. Instead of returning the buffer to the caller, we will have the caller, they're responsible for allocating the buffer, so they could either malloc it or store it on the stack. They just have to give us a pointer to that memory, and they have to tell us how much they successfully read. We will try, same call to fread, we'll try to read from the file into that buffer, and then we'll return true or false based on whether we were able to successfully read something. So if we weren't able to read anything, this function always returns false. If we were able to read something, fread will return non-zero, so we return true in this case. This function isn't going to crash or anything, but actually there are two errors. I started talking about the wrong one first. The first one is we've got a file leak in this function. We open the file up here on the top line, but we never close it. So if you kept calling this function, eventually you wouldn't be able to open files anymore. That part's easy to fix. We just need to remember to close the function, to close the file before we return. But here's what I started talking about a moment ago. I think there's a logical problem with this function, and it has to do with the true or false return. We give the function a buffer, we tell it how much room is in the buffer, but if it reads something successfully, all it does is return true, which means the caller has no idea how much stuff got read into the buffer. If we were reading a string, then we could depend on something like a null terminator to know how much got read into the buffer. But we're not reading a string here. fread doesn't null terminate your array, and unless you know that you're working with strings, null terminating something isn't even meaningful. Here we're reading a bunch of data from a file. We don't do anything to say how much data got read, so even though we fixed the file leak in this function, imagine when this returns to the caller, they've got a buffer, they know that the buffer didn't get overflowed, and they know something got put in the buffer, but they don't have any way of knowing how much stuff is in the buffer. So I don't think this function is really going to be useful the way we designed it here. Maybe a more useful version of this function would return how much data successfully got read. What else do we have? Here, we're going to read not just a buffer worth of binary data, but we're going to return we're going to read a bunch of integer values from the user. And we're going to return how many values successfully got read. We saw a function like this a couple of weeks ago. We're going to make it easy for the function by first, the user has to tell me how many values they want to type in. So the first thing I do is I read an integer from the user, and if they want to enter 10 values, the first thing they'll say is 10. I'm going to type in 10 values. I should have said this already, but the parameter here, length, that's a pass by reference integer that's going to, when this function returns, that's going to contain how many values got read in. So the caller gives us the address of an integer, And then inside the function, we're going to fill in the integer that that points to with whatever, however many values got read in. Since it's already a pointer to an int, when I called scanf, I didn't have to put an ampersand in front of it because it's already a pointer to an int. On my next line, I'm mallocing space for an array to hold however many ints I'm about to read. And here, since len points to the number of integers I'm going to read, I have to dereference it just to compute how much space I'm going to read. On this next line, I'm going to loop through however many integers I'm expected to read. And same here, I have to dereference that. I have to go look at the thing len points to. So I loop over reading all these values. I call scanf to read each one from the user, and I'm doing a little pointer arithmetic. Up here, sequence is a pointer to an int. I think of that as my dynamically allocated array that's got room for all the values I'm about to read. Scanf is expecting, if I say I'm going to read an int, it's expecting a pointer to where it should store that int. So I'm just doing some pointer arithmetic here to find the address of the ith element of this array. And as long as I'm successfully reading stuff, I keep going. If I ever get something that doesn't parse as an int, I pretend the input's garbage, so I return a null to the caller. Otherwise, when I'm done, I return a pointer to the array. So the caller can tell how many values got read because they passed in the address of a place where that value should be stored. So len, or at least len should point to an integer that contains a number of values. And then the return value out of the function should point to an array of all the values that got read. What's wrong with this function? Well, the first one you've had some practice on. There's a path that has a memory leak. If you ever call scanf and get a bad value, we return null so the caller knows this didn't work, but then we leak that memory. And since nobody gets a pointer or gets a copy of this pointer, no one's ever going to be able to free that memory. So on this return, seems like we should free that block of memory. That's easy enough to do. We just need to add a free before we return that error condition. For each of the values here that we read, we check to make sure they got read successfully, but we didn't bother to do that up here. What if the user types in garbage for this first integer? What if effectively I'm expecting them to type in how many values they're going to enter? What if they just type in ABC? Well, this scanf will fail, and that means the thing len points to won't even be modified. Well, depending upon what the caller passed in, that could have garbage in it, which means when I go to call malloc, I might end up asking for 100 billion bytes of memory, depending upon what happens to be in that integer that len points to. That's easy-ish to fix. I can just add code to check that return. And that's what I'm doing here, just like we did every time we read one of these values. I could also check to make sure scanf is successful. And if the user doesn't even tell me how many values they're going to enter, that seems like an error condition, so there also I'll return null. And here I don't have to worry about a memory leak because I haven't malloced the space yet. So this seems like it would work. As long as my user isn't malicious. Here, as long as they enter a nice, reasonable looking value, I should be okay. But what if they really type in a really, really big number, 100 billion or something that exceeds my memory capacity? Well, in that case, this call to malloc is going to fail. And then when I start trying to, and it'll return null. When I start trying to use that memory, though, I'm probably going to get a segmentation fault. All of these that we've looked at so far, I would call programming errors. There were cases where either, we had a potential leak, we just didn't think about something when we were writing a function, or we, or we had at least one case where we kind of have a logical error, a function that didn't really make sense that we couldn't use. Here we started thinking about, well, what if we had a malicious user? What if a user just typed in a value to try to break our program? That would probably crash our program here. Is that something to worry about? I mean, in general, you would say if a user gives you such bad input that it crashes your program, aren't they really just hurting themselves? They ran your program and they got it to crash. So they get their shell prompt back and, well, no harm done. They kind of got what they deserved. Well, I think we have to worry about bigger issues than just whether or not they were able to crash our program. Or let me try that again. If a user can crash our program, they may be hurting more than just themselves. I've run out of time, so let me try to finish this slide real fast. We are probably going to write code that is used by a lot of users. And in some cases, we might write code that runs with higher privileges than the users who are running it. So they may use our programs to do things they couldn't do on their own. And if a malicious user could crash our program or exhibit some behavior that we didn't plan for in our program, they might be able to trick our program into doing things that they couldn't do on their own. And that's where a lot of potential security vulnerabilities come from. If we leave a hole in our program, if we don't plan for potentially bad inputs, even kind of deliberately bad inputs from the user or from another program, an evil user could use this to launch various attacks on our system or on other systems. And that's what we're going to talk about next. We're going to talk about common mistakes and vulnerabilities. But like I said, we're pretty much out of time for today, so we'll have to end it here. I'll look at as usual, I'll look at the quiz that was due for today and see what kind of shape you're in for doing that. And if we haven't covered enough, I'll push that off by a week. I'll go ahead and stop recording, but if people have questions, hang around and ask them, and I'll take them after class.